Hey everyone, and welcome to today's Explainer, where we are breaking down the source material on a massive, honestly seismic, architectural shift happening right now in the world of artificial intelligence. We're moving out of the era of simple, stateless models and diving headfirst into a world where AI is actively managing tools, running complex apps, and operating live websites. And here's the thing, the software foundations we've relied on for a decade, they're starting to crack under the pressure. So today, we're going to look at the brand new engine powering these next-generation AI systems, and that engine is Rust. Here's our quick roadmap for today. We'll start with the AI architecture shift, move into the legacy language bottleneck, explore the Rust infrastructure solution, check out some AI tools and frameworks, look at real-world production deployments, and finally, we'll wrap up with the Python-Rust symbiosis. Let's get right into it. Okay, part one, the AI architecture shift. From stateless functions to stateful agents. Think about the last 10 years of AI. For the longest time, AI models were basically just pure functions. You gave them an input, they did some math for a few milliseconds, and boom, they handed you an output. Super simple, stateless, and ephemeral. If a process crashed, whatever, the system just restarted it. But agentic AI? That is a fundamentally different beast. We're talking about autonomous AI agents that maintain complex context windows, hold open persistent connections to external tools, and execute reasoning loops that might run for hours or even days. They are incredibly, deeply stateful. And the scale of what we're dealing with here is just massive. To put this in perspective, listen to this quote from the research. This shift rivals the transition from monolithic architectures to microservices in its magnitude and implication. When your AI is running multi-step workflows for hours on a live website, the old crash-and-retry philosophy of deploying software is literally dead. Moving to part two, the legacy language bottleneck. Why the crash-and-retry philosophy is dead. So for years, the Python and C++ alliance basically ran the entire AI world, but they are both hitting a massive wall when it comes to agentic AI. On one hand, you have the C++ segfault crisis. C++ relies on a manual memory model. If you've ever spent a weekend pulling your hair out over a random memory leak, you know the absolute misery here. It often leads to catastrophic memory corruption or these awful silent failures where the model keeps running but just spits out corrupted garbage output. And then you have Python's limitations, specifically the global interpreter lock, or the GIL. As any Python dev will painfully tell you, if you have an AI agent that needs to run a web search, query a database, and execute inference all at the exact same time, the GIL puts a harsh, immovable ceiling on that concurrency. When you're building the actual brain of an autonomous system, a 70% risk of memory bugs in C++ is completely unacceptable. Rust totally flips the script here. It drops that down to just a 5% risk. With 95% compile time safety, the compiler literally catches the errors before the program is even allowed to run. I mean, just picture this scenario for a second. What happens when an autonomous AI agent crashes in the exact middle of a complex, multi-day negotiation or some massive data processing task? A segmentation fault isn't just a minor IT hiccup anymore. It's a catastrophic failure of logic and state. Long-running AI agents simply cannot tolerate the memory leaks that accumulate over hours in C++ and eventually trigger sudden system crashes. Which brings us to part three, the Rust infrastructure solution, fearless concurrency and the pit of success. So what's the actual secret sauce here? It's the Rust ownership model. In Rust, every single piece of data has one singular owner. When that owner is no longer needed, the memory is instantly and deterministically freed. No manual cleanup like in C++, and no bulky garbage collector pausing your whole program like in Python or Java. It forces developers into what's known as a pit of success. It's like having a ruthless but ultimately super helpful automated code reviewer looking over your shoulder. If your code isn't memory safe, it simply will not compile, period. And let's look at the numbers, because the real-world performance differences are just staggering. For a multi-step AI agent task, Python takes a sluggish 320 milliseconds to respond. Rust does it in 12 milliseconds. 12! That is literally the difference between an awkward, unnatural voice agent and one that responds in true real time. And the memory footprint is just as wild. Python gobbles up to 400 megabytes just to load the environment, while a pure Rust implementation needs less than 5 megabytes. 10 times. That's the magic number we keep seeing. Across multiple benchmarks, there is consistently a 10x improvement. 10x lower latency, 10x higher request throughput, and a 10x reduction in memory usage.
When you're deploying AI agents at a massive scale in the cloud to run apps and websites, requiring 10 times less RAM and CPU instantly translates to drastically lower cloud hosting costs and vastly higher profit margins. All right, part 4, AI tools and frameworks. A look at the 2026 Rust AI ecosystem. Developers aren't just using Rust for backend plumbing anymore. They're building the entire AI application layer with it. Here are some of the heavy hitters you should know. RIG is currently the top framework for building LLM applications, and it's being used by major enterprises for complex AI apps with multi-turn streaming. Then you have Candle, which is a minimalist machine learning framework from Hugging Face. There's LansDB, providing lightning-fast embedded vector search, and Burn, a comprehensive deep learning framework built entirely from the ground up in Rust. The really cool thing about Candle is that because Rust binaries are so tiny compared to massive PyTorch installations, it can compile AI models directly down into WebAssembly. This means you can run complex transformer models right inside a user's web browser on standard websites with sub-second cold starts. No massive downloads, no lag. It totally unlocks privacy-preserving AI apps that run entirely on the user's device without ever sending a single byte of their data back to a cloud server. Let's move to part 5, real-world production deployments, from Google to Cloudflare. Because look, this is absolutely not just a theoretical exercise. Major tech giants are aggressively putting Rust directly into the critical path of their infrastructure right now. Google actually started adopting Rust for the Android operating system way back in 2019. By 2024, they reported a massive, quantifiable drop in security vulnerabilities. And more recently, Cloudflare launched a custom Rust inference engine to run AI models on their global edge network, absolutely crushing traditional C++ frameworks in speed while using a fraction of the CPU. 0.2. That is the number of memory safety vulnerabilities Google reported per million lines of Rust code. 0.2. Now, compare that to approximately 1,000 vulnerabilities per million lines of C++. For literally any organization building AI infrastructure where a security breach is catastrophic, this single metric is what's driving the entire industry's transition. Finally, part 6, the Python-Rust symbiosis, the hybrid production pattern. So you might be wondering, is Python just dead? Absolutely not. No way. The future is actually this highly efficient partnership between the two. Here's what the modern workflow looks like. Step 1. Researchers use Python's massive ecosystem to prototype, experiment, and train the initial models. Step 2. Engineers use bridging tools like Pyo3 to seamlessly connect that Python code over to Rust. And then Step 3. They rewrite the critical hot path, stuff like token streaming, tool dispatch, the high-throughput server architecture. They write all of that entirely in Rust. It's a brand new division of labor for AI. Think of it like this. Python owns the research lab. Its flexibility makes it absolutely perfect for experimentation. But Rust owns the factory floor. When it is time to deploy AI to millions of users, where memory usage, low latency, and absolute reliability are non-negotiable, Rust takes over. It perfectly mirrors how web development evolved, where developers prototyped in Ruby or Python, but ran the heavy web servers and databases in C. There's this really fascinating philosophical insight from the material, too. It notes that Rust may actually be the best language for AI-generated code, precisely because it doesn't frustrate the programmer. As AI agents increasingly write their own code to solve problems on the fly, traditional human oversight starts to break down. We need a ruthless compiler to catch subtle, catastrophic errors before they ever have a chance to execute. Rust provides exactly that safety net. Which leaves us with one final thing to think about. As AI agents move from being experimental chatbots to fully autonomous entities managing our apps, our websites, and our critical infrastructure, how will you build them? Will your next production AI system rely on the hope that your code won't crash? Or will you build it on the rock-solid foundation of compile time guarantees? Thank you so much for joining me on this explainer. I highly encourage you to dive deeper into the Rust AI ecosystem for your next project, and we'll see you next time.